Welcome everyone. This is another lecture of the subject control system. In previous lecture, I started the block diagram reduction technique, and there we learned about making unity gain of some forward path gain and converting some forward path gain into unity gain, and converting some backward, that means feedback path gain, into some again some unity gain, and then moving of tapping points ahead of a block or beyond a block. Now there are two more techniques, those are moving of summing points. Similarly, moving as tapping point or takeoff point, there is moving of summing point. And as in tapping point, there are two types: beyond a block or ahead of a block. Okay, so let's first discuss about beyond a block. Let's say there is a block G and there is a summing point ahead of this block. Now you want to move this summing block. Let's say for your convenience you need to move this summing point beyond this block. So how you can do this? Look, if the output of this block is y and input is x1 and x2, then what will be the expression for output? X1 plus x2 into g, x1 plus x2 into g. That means x1g plus x2g. So we need to move this summing block, summing point, such that this expression remains valid. That means, let's say now the block is G here and I am moving this summing point from ahead of the block to the beyond of the block. Okay, beyond the block. Let's say I have moved my summing point here, from here to here. Now what will happen? X1 and x2, as it was available for me, it is still available for me, x1 and some line x2. Now what will happen if I feed x2 in this summing block? It will happen, the output y will be x1 plus g, x1 into g plus x2, but that is not the case. The case must be x1 into g plus x2 into g again. So I can use another block having the same transfer function as my main block G, and then I am doing like this. Then the output will be x1 into G plus x2 into G. And again, if it is plus minus, then there is no problem, it will be plus minus. So if I want to move my summing block from ahead to beyond a block, summing point from ahead to beyond a block, I need to add another block of transfer function same as G to use it in the forward path gain of the function x2, of the signal x2. Okay. Now again, let's discuss about ahead of a block. How I can move my summing point ahead of a block. Again, let's say another scenario, I have a block, x1 is the input to the block, there is a summing point after the block, and x2 is another input of that summing point, then that overall output y I am getting. So what will be the expression for y? Y will be x1 into g plus x2. Now let's say for my complex system, to reduce it to simpler one, it will be more convenient if I can move this summing block. Instead of being here, this summing block was here. If this scenario happens to me, that if instead of being here, if this summing block was ahead of this block G, then it would be lot more easier. So how can I replace this summing block and move this summing block to ahead of the system, ahead of the G? It will look like then like this. So what will be the output? Output must not be changed, and I have only x1 and x2 as input. I cannot change my input further. So let's say this is the summing point. Okay, I was getting x1 here and x2 here. Now what happens? Look, it will plus sum x1 and x2, then it will generate x1 plus x2, then multiplied by g. Y will be then x1g plus x2g. But I need x1g plus x2 only. I don't need x2g. So I can multiply. I can use another block 1 by g, and now what will be the system output? Y equals to x1 plus x2 by g total multiplied by g. So it will be x1 x1g plus x2 only. Now this is the output which I want to get. So this kind of scenario, when this kind of scenario arises, I can replace this subsystem with this subsystem. So this is moving of summing point and moving of summing point beyond or ahead of a block. Now let us discuss an example and see how these kind of these techniques are useful for reducing the total block diagram. Let me draw a detailed complex block diagram. There is a summing point. Let us say this is the total system. Okay. Look, I have total 6 blocks G1, G2, G3, G4, H1 and H2 and 3 summing point. Okay, one more thing I need to discuss. I just forgot that summing point, any 2 summing points can be split and tapping points can be split like this. If I have a signal line and I am tapping one signal from this line, and let's say it is going to another part of the total system, that's not important, but I am tapping this signal from here. Again, from this point only I am tapping another signal like this. Then I can represent this portion, this thing as 2 different individual tapping points, because that will mean the same thing only. If this line carries x, then this tapped line will also carry x and this tapped line will also carry x. So if instead of showing these 2 lines in a same tapping point, I can separate these 2 tapping points and I can show this separately. Like again, if this line carries x, then also this line will carry x and this line will carry x. So here there is no situation, no, that kind of situation isn't there. So this kind of thing will not be a problem in this block diagram. But if some situation arises that one tapping point are concentrating with so many points, then those tapping points can be separated like this. Okay, this is another technique. And again, one more thing is this: for summing point, just like tapping point, you can separate summing points. Let's say x1, x2 and x3 is the input to the summing point, and three signals are added together, and output is y. So y will be x1 plus x2 plus x3. Now you can also write this, you can also draw this diagram as comprising of two separate summing points. Each summing point will have two inputs. Okay, let's say this summing point contains x1, and this, from this side there is x3 coming here, plus plus. Now this line will carry, this line here will carry x1 plus x3 as the output line, as the signal through this line. So if I can add x2 here, then the output y will be x2 plus the signal in this line, and signal in this line means x1 plus x3. So the output will eventually, I will have output y is equals to x1 plus x2 plus x3. So if this kind of thing is there and it is becoming harder to actually reduce the system, then you can make these two separate summing blocks like this. Okay, look here, for this block it is not a problem, for this block, this summing point, it is not a problem, but for this summing block, one negative feedback is coming from this side, and one negative feedback is coming from this side. And so you can draw this summing point with comprising of two different summing points. One will take this line and the negative feedback of this line, and then the summation of this line and this line will be fed to one input of the summing point, and this line will be another input of the summing point. So you can break this summing point into these two parts, and that will be a lot more easier to analyze for us. It will be convenient for us to reduce the system. Now I am using I am using techniques one by one. Look, for this system there is a forward path gain, so it will not make any trouble for us. So we are not we are not disturbing this path. But look here, this path is a feedback path having negative feedback. Again, this path is having another feedback path, it is positive feedback path. Again, this path is again a negative feedback path, but you cannot individually evaluate this path, because if you individually evaluate this closed loop, this feedback system using the formula G2 by using the formula G by 1 plus GH, you cannot do that, because there is tapped point between from this feedback path only. So you need to first either convert either move this tapping point to here or here, any portion, then you can analyze. Or one more thing, you can then consider about G2 and G3 to be in cascade. But look here, G2 and G3 is not in cascade, because there from middle there is a takeoff point which is providing to the feedback path. So what I can do, I can move this point here, or I can move this point also in here. So if this point is moved here, then still there will be some problem. there will be some problem regarding this portion. So I am first considering this point to be in here. So if I move this point to here, it will take the thing as moving tapping point beyond a block. What was the situation? If there was a tapping point and there was a block G, and I was taking this signal X as here, so I want to convert this, move this tapping point here. So what I need to do is, I can do this like this. The Y will be still there, X will be still there, and this line must carry X, because this tapped line is carrying X. So this tapped line must carry X, but instead of X, this line carries Y. So I can use 1 by G in order to make the thing, in order to satisfy the thing. If it is X, then it is X into G, Y will be X into G, and it is carrying Y. So if it is 1 by G, then it will be X only, and that's what I need. So if I move this tapping point here, what will happen? I can move this point here from here to here, and I need to divide this signal, signal by G. So it will be, instead of being H1, it will be H1 by this G3. I hope you have understood this portion. This is the first step of our reduction, block diagram reduction. Now the next thing will be, now look, concentrate in this portion. G2 and G3 is now in cascade condition, cascade connection. So I can combine these two. This will give us G2, G3. No problem. Now again, I have this point here. So I want this point to be from here, then that portion, this feedback path will be independent of this portion. So look, if I move this tapping point from here to here, what will happen? It will be H1 plus G3 only, because wait a second, this line, if this line carry X, then what will this line give? This line will give X into H1 by G3. So if I am taking this feedback from here, X1 in X into H1 by G3. So instead of taking from here, I am taking this from here. So I am getting now X only, but I don't need X, I need X into H1 by G3. So I can use this block here, and it will convert this X into H1 by G3. This is the scenario here. Now I can separately, I can break this summing point into two portions. Then that will be two separate feedback system. So let me separate this one. Let me break the summing point. This is plus. This is plus here. this will be minus, and again this will be minus. Again, this tapping point can be separated. So this portion can be considered an independent closed loop system, independent negative feedback system. So this portion, this is the forward path, this is the forward path, and this is the reverse path. So what was the formula? The forward, if the forward path gain is G and the reverse path gain is H, then the formula was like this: G by 1 plus GH, if it is negative feedback. So it is negative feedback, yes. So I can replace this total thing using G2 G3 by 1 plus G2 G3 H2. The forward path gain is G, so G here, the forward path gain is here G2 G3, so G2 G3 here, and the reverse path gain is H. So I can replace this one G2 G3 by 1 plus G2 G3 H2. Okay. So till now it is simple. Now again, this portion is another negative feedback system, and again I can reduce this portion. So forward path gain G2 G3 by 1 plus G2 G3 H2, total by 1 plus H1 by G3 into G2 G3 by 1 plus G2 G3 H2. So the total thing is G2 G3 by 1 plus G2 G3 H2 by 1 plus G2 H1 by 1 plus G2 G3 H2. Now again I can simplify further. This will look like G2 G3 1 plus G2 G3 G2 G3 G3 H2 G2 G3 H2 plus G2 H1. This is the total transfer function of this portion. So let me replace this with this block. G2 G3 by 1 plus G2 G3 H2 plus G2 H1. Again, these two blocks are in cascade, so I can write it as here as this. Now one more thing, this total portion can be now positive feedback system. So what is the formula for positive feedback system? If G is the forward path gain and H is the reverse path gain, then the total transfer function would be C by R equals to, this is positive feedback, so it will be G by 1 minus GH. For positive feedback it will be minus. So let me calculate this. So forward path gain G1, G2, G3 by 1 plus G2, G3, H2 plus G2, H1 by 1 minus of H1 by G3 into G1, G2, G3 by 1 plus G2, G3, H2 plus G2, H1. So G3, G3 can get cancelled and the total system transfer function will be then G1, G2, G3 1 plus G2, G3, H2 plus G2, H1 plus minus G1, G2, H1. This will be the total transfer function of this portion. So I can replace this closed loop feedback, closed loop positive feedback system with this transfer function. G1, G2, G3 by 1 plus G2, G3, H2 plus G2, H1 minus G1, G2, H1. And the last thing that is to be needed is this line and this line are parallel, so the total transfer function will be G4 plus this portion. That means the total answer will be plus G4. This is the single block diagram. Let me draw the block diagram. Single block diagram. G1, G2, G3 by 1 plus G2, G3, H2 plus G2, H1 minus G1, G2, H1 plus G4. This is the overall transfer function of the system. This is the overall transfer function of the system. So the system I had taken as a complex block diagram, and as a whole that system was so much hard to actually analyze. So we need to first reduce that complex system into a simpler block diagram. Then we can easily analyze by analyzing this transfer function only. You can easily analyze the system. Okay, one thing that may be confusing for you, that I have done one thing here. There was a portion like this. There was a portion like this. It was G2, G3 as I can remember, and here it was H1 by G3. Okay, and the tapping point was here, and I convert this tapping point from here to here, and I used H1 G3 as a block here. So the confusion may arise that if I have a block G and I am tapped some signal X from here, then I am moving this tapping point here. So I need to do this kind of thing. The G will be there, the tapping point Y, the tap point will be Y. So to get X, I need to divide by G. So whenever I am moving the tapping point in this direction, I need to divide G. But instead of dividing by this block, by this block transfer function, I am multiplying this by this transfer function. Why I am doing that? I am moving this tapping point from here to here. So why I am doing that? Look carefully. Here the path was forward path. So from this side to this side, this was input side and this was output side for this block. So the movement was from ahead to beyond the transfer function G. But what is happening here? The path is in reverse direction. The path is in reverse direction. So this point is beyond H1 by G3 and this point is ahead H1 by G3. So what would it be if it is ahead? If the movement is ahead, if it is G, and let us say I have tapped from here and I am moving this point to ahead of G, X, Y, that means XG, and I am getting Y here. So what I will do is I will actually multiply this signal by G, isn't it? Why? Because I need Y as tapped point, but I am getting X as tap point here. So the tapped signal must be Y. So how we can get Y? I can multiply it by G. So don't consider the direction, whether the movement is, the tapping point is moving from left to right or right to left. That is not the concern. Think about the path here. This portion is analyzed in this direction, that means in rightward direction, and this portion is analyzed in leftward direction. So always consider the direction of the arrow. This arrow, the arrow, if your movement is against your arrow, then that is called moving to ahead. And if your direction of movement is with the arrow, same as the arrow, then that will be called as beyond. So for beyond, the block transfer function must be divided, and for ahead it must be multiplied. So though the tapping point from left to right is moving, but the arrow is in right to left direction. So it is not movement towards beyond the block, rather it is movement to ahead of the block. As it is movement towards ahead of the block, that's why the multiplication is happening, not the division. Now if there was tapping, if there is tapping point here and I am moving in here, then that would be beyond the block, because the signal is coming from this side. Now my tapping point is here, so look from here, the tapping point is beyond the signal, beyond the block. You always run through signals. Now this signals is running in this direction, so this tapping point is beyond. So if I move this tapping point from here to here, then that will not be moving towards beyond, it will be moving ahead of the system, okay, towards the input side of this block. So I thought that there may be confusion for this portion, what I had just done during the reduction technique, and that's why I am explaining these things. I think the time is over, so I cannot start signal flow graph today. SFG will be started tomorrow onwards, and tomorrow's lecture can be the last lecture of the subject of this chapter basics, or maybe one more video will be there. So why we need signal flow graph? As you can understand, I hope that any complex block diagram reduction is much more time consuming. As you have seen, as you have just seen, that one complex block diagram I have taken, and to reduce it to a simpler one, I need of the total lecture time. So it is not convenient for all the control engineers every time to do this kind of steps and these kind of things. So they actually convert this complex block diagram into first into signal flow graph, and then from signal flow graph there are fixed formula, and using that fixed formula, by just literally one step, you can convert the transfer function, you can arrive to the simpler transfer function. Okay, so signal flow graph will be started from tomorrow onwards. Thank you. This much for today's lecture.